I hope my screen is visible to all.
Yes, ma'am.
Yes, ma'am.
Okay, so this is a class. It is about mapping and developing land use and land cover using remote sensing image and processing about it. So it is data generation using the RS. So you know about this is a lab. So here we will be talking about two major contents. One will be mapping and developing land use and cover image using the remote sensing image processing technique. And the second part of the class will be about transport applications. And they will involve two mini project submissions from your side. So I hope this part is clear. So next is we begin with the basic concepts of remote sensing. And these things you have already learned in your remote sensing class. So we'll just go a brush up through it. So the first is about understanding of what is remote sensing. So it is acquiring any kind of information from a remote distance or from a distance. So there are two examples of it which I have discussed here. One is the human eye. It is a visual system and it is also an example of remote sensing in a general sense. And the next is the techniques used by bats. So this is echolocation. So bat emits sonar signal and they use this to locate their prey, potential prey, because when it gets obstructed in the past, they are able to identify okay where the obstruction may lie. So these sensors, like here, when we talk about in the terms of sensing of real life objects or the landscape, so the sensors can be mounted on various platforms or altitudes. They could be space-borne sensors, you know about the satellites. They could be on the aeroplanes. It could be fitted on any air-based sensors. Then there are sonars which monitor ocean floor. Then there could be earth-based sensors. There are drones, etc. And how basically they sense, they do away with the information that they extract is they send back to a data download dish that is located at various stations across the earth, and then they are stored whether in supercomputers or they are stored in clouds nowadays. So this is the remote sensing process in general. So the sun, it acts as the medium of energy in the earth, on earth, and then on the basis of this the sun rays, they pass through the atmosphere, they reach earth and they are reflected by or they get a different reaction from different body types that are present on earth, which is then received by the satellite. The signal is then sent to the antenna receiver, and on the basis of that is extracted by the computer analyst, and it can use this in several applications, land use, land cover. So this is the entire process of remote sensing. So mostly we will be concerned to the visible part of the spectrum and infrared, but other radiations are also useful for different things, like UV radiations are for mineral properties, microwave for surface roughness, moisture content, so they can be used. And basically the visible portion of spectrum is also responsible for color. So the objects that they reflect, the color that they reflect are usually the color that we see. Like for example, for plants, they reflect green, or they reflect in the wavelength that is predominantly between 0.54 micrometers. So we observe the objects as the color they reflect. So, therefore, talking about what is the interaction of this energy with the Earth's surface. So, for this is important because we need to capture the information of land and water in our application. So, that is why this entire spectral reflectance curve, and to understand the property, how the reflectance happen among different types of objects is important, or different types of surfaces, I may say, is important because it tells about surface characteristic, the proportion of reflected, absorbed, or transmitted, because these are the three states in which the lights may or the energy may behave. It may get reflected, absorbed, or transmitted. So it varies with the wavelength and material type. So we try to understand first for vegetation. So vegetation, we see that the reflectance is very low in case of this blue and green, blue and red, just because of the presence of chlorophyll in this absorbs more of blue and red light. So it reflects more in the NIR region. So when doing a performance to understand the state or character of vegetation, we may try to include NIR band for a enhanced identification. So it can be used, for deciduous and coniferous identification, or it could be used to understand healthy vegetation and high reflectance. The next is about the soil. So soil, the reflectance, we can see it is mostly in the SWIR region, that is short wave infrared, and they vary on basis of different soil character. It could be, moisture content present in the soil color, the presence of minerals. So it varies on the basis of that. The next is for water. Water, we can see that it has very low reflectance when it is compared to the vegetation and to the soil, but it has a total absorption, or it totally absorbs it in the NIR region. So that is where we use this NIR region for identification of water bodies. So it completely appears black. So now how do we actually sense? How do we actually identify the objects or the features? So this is on the basis of the color sensing. So there are three primary colors, or we can say additive colors, which are red, blue, and green. So we know the VIBGYOR, and they together they forms the white light. So or the white color. So this is any computer screen or any kind of television what you see that they are made of these reds, green, and white components, and then on together you try to identify, or you give different colors. So on the basis of this, all the colors are generated. Now the next is the negative color. So this is used in the print media. Just a moment. Madhumita, please, class is going on. So next is the negative color that is used in the print media. So here basically these colors or this are used as a filters. So cyan filters red, and yellow it filters the blue, magenta it filters the green. So if suppose both the filter color or both the negative colors are put together, they together filter both red and green, and thus you will have blue as an output. So this is how while printing or in your printers, these colors are used to as a filters to obtain the real image or the picture of it. So what happened in satellite, like the satellite, if you can see there are, it captures data in various bands, maybe in the, or you can say in the wavelength. It could be in the visible blue, visible green, visible red, near infrared, mid infrared. So there are several bands of it. And human eye is or can only visualize things in the visible zone, or the BGR, or the VIBGYOR composition. So an image, it is said to be in a true color composite when it is has these three visual primary colors, that is red, blue, and green. But some objects they perform, or they reflect better when they are in the near, or when in the near infrared zone or in the mid infrared zone. And for that we need to make a composite, or we need to make a band composite or an image composite, such that we can identify easily their reflectance. So here we use this false color composite. So what is a false color composite? In which artificially generated color image is produced, in which blue, green, and red colors are assigned to the wavelengths where they actually do not belong. So here if we use this, suppose green, red, and near infrared, and we assign blue, green, and red color to these, so this will lead into the development of FCCs. Now next we will be like you will get a more clarity about this. So these are the raw bands of Landsat. So you can see all the images are in grayscale. They are grayscale images, but you can assign the color. So if the true colors are assigned, that is red, blue, and green are assigned to the respective bands which they actually belong to, then we observe a TCC. However, if these colors are assigned to suppose green, blue, and NIR, so then we observe something called FCC. So you can see some portions are coming as red, which are actually not that looking like that. So you develop an FCC based on your requirement. the features you want to extract and where in which band they have the maximum reflectance, or they are more identifiable, or they are characteristically different. So after till here, I hope there is no doubt. Okay, then we shall move to the next part of it. So the next part is about the remote sensor. So we know that a remote sensor can be mounted at any platform. So it is a device that detects the EM energy and then it quantifies it, and it usually records it in an analog way or a digital way. So what is the the usual camera that we used to have before, when the times when we used to put reels and click pictures. So what it used to do, it used to contain the crystals of silver halide. So basically, it used to work on chemical reaction. The basic principle of it, that when the light energy would fall on it, it would the particles would react differently, and then a image could be produced. However, in digital cameras or in a multispectral scanner, there is electronic detectors which are made of semiconductor materials, and they can also be called as charge coupled device, and they are sensitive to this light energy. And they are also capable to understand, okay, or they are capable to store the amount of energy. They are capable to measure the amount of energy that falls on each of the cells. So this measurement is reflected in the terms of numerical value, or what is digital number, what we call it as digital number. The image, you can see it here, like it has a binary, it's a binary image, and if the smallest part, it contains value for each element, and the smallest element is called pixel, which contains the digital number value. So this image is this way of capturing image, or the digital image is has superseded the film type of image capture. It is because film cannot capture EMR which is beyond 1 micrometer, which is in the microwave zone, and then it is not possible to produce and store large amount of films from the satellite. Also, the solid state device, they are electronic and they are very reliable, and they use very little power. They are small and easy, basically easy to use. And then the data that are obtained also is easily transmitted, and they stay for a long time without any degradation. And also the digital data are in the form that can be readily processed. Like, since they carry this digital number value or numerical value, they can be processed in computers. However, the other forms cannot. So that is why digital data is important. So what is digital image? So basically it is an image that can be defined as it has a two-dimensional function, which is fx and y, and x and y are the spatial coordinates where it is located in the spatial plane. And again, it is further divided into illumination and reflectance coordinate. So illumination is just characterized by the light source, and the reflectance is just characterized by the object, whether it is taking a total absorption or it is giving a total reflectance. So this is how a digital image would appear. So you can see this is a digital image, and somehow this it will look in a mathematical form. So the right side of equation is a digital image by definition, and this every element here in this matrix, it is called a pixel. So this is how a digital image would look like. Now next, from here, we'll be trying to understand the pixel capabilities or the pixel resolution by relating it to sensor resolution. How with different sensor resolution, what are the pixel qualities it might have? So are there any doubts yet? Or is it that I have been too fast? Okay. Sir, shall I move to the next part? The resolutions? Yes.
Move forward.
Sorry?
Move on.
Am I
Yeah,
audible?
I think you can
just
continue.
just
ask them,
There's no
and
one.
if there are any questions, then first let them clear it
Yes.
out. Because I don't know whether there are some people who have not understood remote sensing or who have not attended remote sensing classes may be able to understand the FCC and TCC. So see students, if you don't understand it properly, then you will not be able to do any project for sure. So if you are, and most of you, at least 90% of you, as we have seen in last 4 5 years, use at least one part of this particular lab in your thesis, at least for map making. Okay, so please understand everything carefully. Okay, other than this one theory class, we are not going to repeat again a theory class. You understood? So if you have doubts, you ask. If you are muted and if you sit as you are now, so it is your loss. That's all. That's all I can say. If there are no questions, Aishwarya, you are free to go.
Okay. Are there any questions regarding anything? Like we spoke about the spectral reflectance curve. We spoke about sensors. We spoke about the color
Ma'am, can
scheme.
you tell about the digital number? Can you explain it a little? Digital number.
Okay, digital number. Digital number, it can be anything. It could be the brightness level. It could also be the height. It could be any information that satellite would capture. So once it has captured using a digital, using this semiconductor device or the charge coupled device, so it assigns, it captures it quantifies the value of the reflectance. So it gets stored in those features. So that appears as a digital number. That appears as a
It's stored in form of 0 1 only, or it can be any.
no. It could be 0 1 when I'm talking about 0 1.
I just
Zero
saw the
one.
slide, that's why I
Okay.
asked.
Yes. Wait, just a minute. Okay. So when I'm saying here this 0 1, it is basically a binary image. Okay. So this has data in terms of 0 and 1, but it could be an image which has more number of brightness value or more number of grayscales value. Then the image, then the values may vary. Uh, so we will be talking about, when we talk about various kinds of resolution, you will be able to understand कि there could be images in different gray levels that could be stored. So this is just an example. However, if you can see this one, this here you can see there are a lot of values, different number of values. So this is on the basis of the gray level for that picture, the extension or the, you can say the limit that picture captures.
Okay, thank you.
Anything else? Did you understand this FCC and TCC, how we do TCC and FCC? Everyone?
Yes, ma'am.
Okay. So this will be, very important for you because what you will be working on is a land use extraction. So there your main features of extraction would be land use, water, vegetation. So you will have to select the bands carefully based on your application. So that is very important. So that time you will be requiring to make a false color composite. So please, even if now you are hesitating, read through all these aspects because this will be important in continuing your thesis as well. Because most of you, as sir said, will be taking maybe this GIS as one of the means for your analysis. So okay, next I move to sensor resolution. So now we have understood that sensors are mounted at different platforms. So we talk about the satellite sensor resolution. So the first kind of resolution is the spatial resolution of a sensor. So when we talk about spatial resolution, it is, you can call it the edge length of a pixel or the pixel size or the amount of data every pixel captures. So you can see in the first, it has captured almost 30-meter data in a 1 pixel. Like if you can visualize 30 square meter, like the area, it is captured within 1 pixel. So if a house is within, or it can capture more than that, so the pixel outcome that you will look in the satellite image would be something like that. There will be no defined edges to the house just because it has very coarse resolution. However, as you exceed, if you get a finer resolution data, which has captured only 5 meters of data for the house, maybe the display could be something like that. You will be able to identify or locate things better and properly. So this is a finer resolution pixel that you may get. The application may vary depending upon, I mean to say your requirement may vary depending upon the application you want to use. For example, the next is 1 meter. So you are now getting a more finer image of the object that is captured. So the measurement of the resolution is the edge length of the pixel. The higher the resolution, the finer is the grid, and larger is the degree of recognizing detail of the object that you are looking at. So based on the spatial resolution, satellite systems can be classified as follows. There could be very low resolution satellites, MODIS, like it has 250 to 500 meter data that is captured within a pixel. Then there are medium resolution systems which capture like 50 to 70 meter data. Then there are very high resolution system like Landsat, which you may be using in your analysis part. So it covers like 30 meter of data. It has a spatial cover. Then very high resolution system like QuickBird and all. So it has 2.4 to 2.8 meter resolution. So maybe you can see a car significantly, you can see a house, you can see roads. So you can distinguish between, these things there very, very clearly. So next in sensor resolution is the spectral resolution of the sensor. So spectral resolution is the number of bandwidth, or the higher the number of bandwidth of a remote sensing sensor, highest is the spectral resolution. So number of bandwidth it is able to capture, the sensor is able to capture. It defines its spectral resolution, like why, if it has more number of bandwidth or it can capture within different number of bandwidths, then you can use it in various applications. It will be since different objects, they behave in differently in different bandwidths, so you can use those data for your distinct application. So example, IRS list 3, it uses 4 bands. So it is in green, red, near infrared and mid infrared. However, in MODIS, there are almost 36 spectral bands. And if you see hyperspectral sensors, they have very narrow spectral bands, more than 100 spectral bands. So this is how it can cover in different spectral bands. So it has this is what spectral resolution speaks about. So next is the radiometric resolution. So this is what we are talking before, like it is about how much bit depth the data has. So radiometric resolution of a sensor is measure of the gray levels that are measured. So it could be, like just pure black and pure white, like black with no reflectance and white with the total reflectance. So like that kind of, and then on the basis of that, it could be 2 levels, it could be 128 levels if it is 7-bit, it could be 256 levels if it is 8-bit, it could be 2048 levels if it is 11-bit satellite, resolution, radiometric resolution. So it will be able to, you will be more distinctly able to identify the image. So this is, I'll be showing you the image, how you can, see. So this is a 2-bit data, which is a coarse data. Now with the 8-bit data, we can see more depth has been added to this data. So you can more distinctly identify characters in the image. So this is what radiometric resolution is all about. So next is the temporal resolution of a sensor or a satellite. Temporal resolution is when when the next satellite visits or revisits the same place. Like it has visited India today. Now after 16 days, again you will get a data. The next 16 days, again you can get the data. So maybe if it visits like every 16 days, your analysis would vary. Like you can need some like for a land use analysis, you may be needing for every 5 years data or every 10 years data. So you have to see at the same season when your satellites revisits the place. So it is a temporal resolution varies. It could be 1 hour or it could be approximately to less than 30 days. So like Landsat, it has 16 days. It can it revisits the same place after next 16 days. MODIS, you can have daily data. So this is how they temporal resolution is all about. So I hope this part is clear to everyone. Okay. So moving towards one of the satellite as an example, this is Landsat satellite. So these are the several missions that have been launched. The recent one is Landsat 8, which was launched in 2003. And it has three sensors, OLI, which is 30-meter resolution, PAN, that is 15-meter, and then thermal infrared sensors, which 100-meter resolution. And it revisits 16 days at the same place. Now this talks about the spectral resolution that it covers. So it covers in this blue and green, then red, and up to mid-infrared zones, wavelengths it cover. It captures data in all these spectral resolution. So the first section we finish here. So we'll be moving to the next section about the maps. So I hope this part is clear to everyone till here.
So did everyone who haven't taken this subject understood what resolution means? Has everyone understood? So I'm asking you again and again. Then when you are given this one, don't say that I did not understand. I think they are either sleeping or I've understood everything. So you go ahead.
Okay, or I shall go ahead now. Next part also, sir, or wait for.
Yeah, you get. Go ahead. Go ahead.
Okay, okay. So now we will be talking about maps. Like after you have captured the data is acquired from the satellite, then how they are maps are developed, or what is map? So map, it is a plane that represents the Earth's surface and it has a definite scale. So how we assign scale to the map? So map scale is basically the ratio that is distance on the ground and which is comparable, what is the corresponding distance on the map? Like it is the ratio of that. So scale is also called as a representative factor. Now next we can see. So you see here when we talk about the globe distance in respective to the Earth distance. So what is the representative factor of the globe? So that we can see it is in 1:24,000 scale. Similarly, when the globe, it is projected as a map on a flatter surface, then the map projection or the scale factor is 0.9996. So this is in reference to what is the distance of the map or the distance of the globe in respect to the distance of the Earth. What is its distance on the ground? So there are different map projection system. So map projection is basically transformation of any spherical or ellipsoidal Earth onto a flatter surface on a flat map. That is basically we call map projection. And it eases us basically to help to identify the locations and to do like a common system has been developed so that everyone is on the same page wherever people works on map. They use a common reference system or a common mapping system so that it is much easier to understand and to develop maps. So the map projection system can be made on a flat surface, on a surface that can be made flat by cutting it as a cylinder or a cone. So we will see how they have developed on by understanding how the map can be represented as using a cylinder or in a conical shape. And if the globe after scaling cuts the surface, so that projection is called a secant. And lines where the cut takes place, that surface that takes place is called, like wherever that surface will touch, it will have no projection distortion. That will be the ideal area, or that could be you can say that can be projected without distortion. So this is the cylindrical projection. So we call it transverse because we use it in this way. That is why it is called universal transverse Smeaton. The next projection systems are conical projections, basically used for the polar regions. So you can see this is the second part of it. And the next is the azimuthal projection for polar, for equatorial, and for oblique regions. This has been shown. Now we'll be describing universal transverse meticker in detail because this is the system which you will be using more uh, like more frequently. So UTM, it stands for Universal Transverse Meticker, and it is a geographic coordinate system, and it gives a location on Earth in meters, and it divides like the 360-degree. It is divided, the entire Earth. It is being divided into 60 zones with 6 degrees longitude with each. And this 1 to 60 degree, this is begins at 180-degree longitude, and it moves ahead with the east, like every it goes on 1 to 60. And then the UTM zone, it extends from this 84 degrees north to 80 degrees south. And the zones that are located above the equator, they can be called as 17 north, like they have this N as the designation, and which are below the equator have S as south as a designation. So next is the lat long coordinate system. So in lat long coordinate system, which is also known as geographic coordinate system, so it is referenced by longitude and latitude. And longitude and latitude are nothing but are angles that are measured from the center of the earth. So those are measured in mostly in degrees. So they are often either measured in degree, decimal degrees, or they are represented in degree, minute, and seconds. So you can see here the UTM zones in India. So it is from 42, 43, 44, 45, and 46. Also importantly, you can, if you know the longitudinal value, you will be able to understand which UTM zone the country falls into. So you have to take a small equation, and on the basis of that, you will be able to understand which UTM zone it will be located in. So now the second part also we have finished. It is about the projection and coordinate system, which are necessary to acquire the data on the ground. And now we will be more moving towards what are the land cover and land use metrics and how they are done and what are the algorithms used. So this section also is any doubts up till here? I hope everything is clear to you.
Yes, ma'am.
Okay. Okay, sir, shall I continue then the next part also?
Yes, please. If you want, you can take a 5-minute break so that you can take some rest and then start.
Okay, okay, then 5 minutes break it is. Just come back at 45 at 2:45. Okay, I guess everyone is back. So next, we'll try to understand how we extract land cover from the land use from the satellite data. So land cover is basically it is the observed biophysical cover of the Earth's surface. What you observe, it is the natural cover of the Earth's surface. So land use indices, there are two indices that we will be talking. I hope I'm audible to all.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So the first indice that I'll be talking it it is the NDVI or Normalized Differentiation Vegetation Index. So it is a standardized way to measure the healthy vegetation in the region. So this what the result of this formula, it is generated between a value of -1 to +1. So we can see here there are two plants. So one is a healthy and a stressed vegetation. So since it uses NIR and red, and we know that a vegetation that has maximum reflectance in NIR region. So the difference has been used to develop this NDVI formula. So it quantifies vegetation by measuring the difference between the near infrared, which vegetation which strongly reflects in that zone, and the next is the red light, which vegetation almost absorbs. The next index that we'll be talking about is normalized difference water index or NDDWI. It is related to the plant water content. So the amount of water that is available in the internal structure of a leaf or in the plant, it largely controls what is the spectral reflectance in the shortwave infrared or SWIR region. So interval of the of the of that SWIR region. So it is therefore very good proxy for a plant water stress if you want to understand. So this uses two bands. One is the NIR band and the SWIR band. So it is also a dimensionless output. It also gives a dimensionless output that varies from -1 to +1. So we can see as the increasing water content. So the blue increases. So towards the positive side, it has that means the water content is higher, and toward the negative side, you can understand it is in stress or it is a drought-like condition or something like that. So these indices are very important for a quick understanding of the region. So you can use it to understand the overall spatial variation. So after we have analyzed the land cover part of it, we would like to go into further detail by looking into the land use, like what are the features which are present in a particular area of interest or a location. So what do we understand by land use? And it is also an objective that you will be working on this subject, or this will be the output of this class. So here we try to automatically categorize the pictures in an image into a theme or in a class. So what we mean by theme is like you are interested in a certain kind of category. It could be a water, agriculture, wasteland, urban land, forest land, various categories. And how they are classified? They are classified on the basis of the spectral pattern which is present within the data, that each pixel, what is the spectral pattern that it reflects. So it is going to be distinct for water, for agriculture, for wasteland. It is going to be distinct pattern, and thus that is how it helps us to get classified into different groups. So it is used to perform the classification, and indeed the spectral pattern present within the data for each pixel is used as a numerical basis for these categorization. So you can see here they have categorized it, color coded it using different, like two prominent classes. What we can see here is the forest land and the agriculture, and some part of wasteland can also be seen in this part. So they have done a temporal analysis to understand it. So the classification levels, it can be enhanced, it can be varied. Like the first level could be you identify the urban or the built up land where you can extract it. You can go further by identifying the residential, various land use types, basically the residential, the commercial, the industrial, the built up land, or any other mixed land use which exist. And the next could be further probing into the residential part of it, like looking into a single family residence or a multi-family, or what is the mobile parks, or what is the transient lodgings. So classifying it into as the your like level of detail increases, so thus the classification details also increases. Now this classification or the extraction can be done in two ways. One is the supervised classification. In supervised classification, basically the analyst or the person who is analyzing the image, it supervises the pixel and categorizes by the process of specifying to the computer what algorithm it wants and numerical descriptors of various land cover, land types present in the scene. So basically it takes some training data set or from each of the classification or the each of the classes that it is interested in, like some training data set from urban, some training data set from, let's say, vegetation, let's say the water category, and on the basis of this the algorithm functions and it identifies or it groups the other pixels to these three identified class. However, in unsupervised classification, the image data are first classified by just aggregating them into their natural spectral groupings. Like if the two spectral groupings seem to be close, they are first naturally agglomerated or they are aggregated into those groups, and then they are iterated and the classification pattern is improved. So in detail, if we see supervised algorithms, they are like one is the simpler one is the minimum distance to the mean. So every pixel, it is assigned a class or a base or a distance from the mean. So the one which is closest to mean is grouped into that class. Like if the mean is closest to the mean of the class, it is automatically grouped into that class. The next is the parallelopiped or the blocks classifier. Here, on the basis of standard deviation, different boxes are assigned or are taken. So the pixel which is the limitation is like the pixel which is outside to the box is not classified, it does not get assigned any class to it. And also which the pixels that are that fall into overlapping boxes, they may also be, left unclassified. So here maximum likelihood classifier, it is identified as one of the most robust classification techniques in supervised classification, and it assumes a normal distribution for its training data sets. So once you train your areas or once you train your data set, it generates probability contours next to it around your training data sets, as you can see here. And the pixel is assigned to a class depending upon the value of that probability contours that it encompasses it. So it is generally the most powerful, it's considered as the most powerful classifier. However, how it happens in unsupervised classification, so it just groups the pixel. So such as ISO data clustering or something, it requires a maximum number of classes. Then it requires a maximum number of iteration, and it iterates till the threshold is achieved or the threshold value comes. So initially it assigns just a arbitrary mean to the classes, and it allocates or it groups all the pixel on the image to the class to it is the mean is closest. So once it is grouped, again it goes and it again assigns the mean, and it is recalculated for each pixel, and again it is put into the new class means. So this procedure, it is repeated over several iterations unless it reaches a particular threshold. So here, so one of the techniques, like mostly the supervised learning techniques, will be the one which will be you will be doing for your land use classification in the coming classes. So next we will try to understand the SOI maps or the Survey of India map. So these are the topographical maps. We required them just to understand the spatial location of any area that we are working on or our area of interest. We also use them for georeferencing, etc. So everything will come in the, you will be doing practical on each of this by understanding it and locating it to your area of interest. So you will be doing it. So now basically first we have to understand the features of the map. So how does a map look like? So a map is going to have a map body, whatever the data it is or the information it is going to share. And then it is going to always have a north arrow to understand, okay, what direction, which direction it is, an indicative of direction on the map. Then it is a scale bar that we have discussed till now, the representative factor of what is its true scale on the earth. And then a title bar, what kind of map it is. It is India's map, or it is a state level map, or whatever title that depends upon the map body. And then comes a legend or the index, that is basically it is a buffered area or it is a boundary, whatever it is. And then the coordinate system, uh, it could be on lat long, it is in degree, minute and seconds. And then the map index, if you produce a key map to show, you know, the location index where it is actually located in the large map of India. So you can do that. So again, we talk about the scale of a map in detail. So it is basic requirement. It must be present. A map is not complete if it doesn't have all the map body which is mentioned. So it has a basic requirement for preparation of any map or any plan. Scale is used to represent large distances on paper, and it is the ratio of distance on map corresponding what is on the real ground or earth. So this is the representative factor, and you have to estimate it on the basis of this ratio. So the next, we would look into detail in the map numbering system. So India and adjacent countries, it has the sheet covering of India, which has maps from 39 to 92 numbers. And each sheet is bounded by a 4° to 4°. Like all the map, the square part of it, or the each sheet number is 4° to 4° in dimension, and it represents 1:1,000,000 scale. Okay, so example, we will be detailing out the map number 53 here. So when we see the map number 53, it is further divided into 16 parts, all 1° to 1°. And this has a scale of 1:25,000. So when we talk about this, we write it in the terms of 53 north. So these are called degree maps. So each of the section is 1° to 1° lat long. So now it is further divided into 16 parts, and this 16 parts is 15 minutes to 15 minutes. And here it is numbered again from 1 to 16. So, and it is the scale all these maps would be having is 1:50,000, and they would be written as 53B, and then again the map that you select, the section or the tile that you select, that this tile is 3. So 53B/3, and these are called quarter degree maps. So again, they are further divided into in 7.5 minutes to 7.5 minutes, and they have the scale of 1:25,000. Now they are further divided as northeast, northwest, southeast, and southwest. And when you write them as 53, which is for the main map, then O/14 northeast, because you are selecting this O tile, and this is the northeast of the 14th tile in it. So this, here we come to the end of the first class. So we have covered almost all the basic things that you will be requiring for doing the practical sessions that is involved in this subject. I hope there are no doubts, and if there is any doubt, please ask. Because we will be moving forward to not data downloading, but downloading